Somewhere in Southern California, a mountain pass stopped an earthquake in 1857 and let one through in 1812. Same rock, same fault junction, two different outcomes. Now scientists say the ground beneath that pass has hit a stress level unseen in 1,000 years, and they found something in the data more disturbing than the number itself. The two faults meeting there are no longer stressed at different levels. They're converging. Researchers call this junction an earthquake gate. What decides whether it opens or stays shut has nothing to do with how big either fault is on its own. The place is called Cajon Pass. It sits northeast of Los Angeles, a narrow gap in the mountains where Interstate 15 climbs through, where freight trains cross on their way to the desert, where power lines and fiber routes run because the terrain leaves almost nowhere else to put them. Underneath all of that, two of California's most active fault systems come close enough to touch. The San Andreas Fault runs through on one side. The San Jacinto Fault runs through on the other. And a new study published this year in the Journal of Geophysical Research, Solid Earth, by a team led by geophysicist Liliane Burkhardt at the University of Bern, says the stress sitting on those faults right now is higher than at any point in the last 1,000 years. That number alone should get your attention. But it's not actually the headline. The real finding is stranger, and it has to do with how these two faults behave when they meet. Picture the pass itself for a second. It's not a dramatic canyon. It's an ordinary mountain gap, the kind you drive through without noticing, semis grinding uphill in the slow lane, a freight train running parallel to the highway on tracks that have carried cargo through here for more than a century. Engineers who designed that infrastructure knew they were building on active ground. What none of them had until this year was a working model of exactly how the pressure on either side of that ground compares right now. Here's the obvious story, the one most people would assume. California hasn't had a major rupture on this stretch of the San Andreas since 1857. That's the Fort Tejon earthquake, magnitude 7.9, one of the largest in the state's recorded history. 169 years is a long time for a fault built to move constantly to sit still. Strain doesn't disappear just because the ground stops shaking. It keeps accumulating silently, year after year, the way pressure builds in something sealed shut. So the natural assumption is simple. It's overdue. The clock has been ticking since 1857, and eventually physics wins. That part isn't wrong. Faults really do work this way. Two plates grind past each other along the San Andreas boundary. They catch, they lock, and the motion that would normally happen smoothly instead gets stored as tension in the rock. The way a rope pulled tight against a stuck knot keeps loading force into the fibers instead of sliding free. The longer the lock holds, the more energy waits to be released. This is basic, well-established science, and it's the reason seismologists have watched this stretch of California for decades. But overdue has failed before, and it's failed in ways that should make anyone cautious about treating elapsed time as a countdown. Along a different stretch of the San Andreas near Parkfield, seismologists spent years expecting a moderate earthquake based on a seemingly regular recurrence pattern. Official forecasts put a window on it, and the quake didn't arrive until more than a decade after that window closed. Elsewhere in the state, quiet periods that looked alarming on paper have stretched on for decades without producing the expected event. Elapsed time by itself has never been a reliable predictor of when a fault will fail. If it were, seismologists would already have solved earthquake forecasting. They haven't. So while the "it's overdue" explanation captures something true about accumulated strain, it can't explain the detail that actually makes this new study different. Because overdue doesn't tell you what happens once a rupture starts. It doesn't tell you where it stops. And that's the detail the researchers went looking for. Because Cajon Pass has a strange history. In 1857, the Fort Tejon rupture tore through more than 200 miles of the San Andreas, and then it hit this junction, and it stopped. It never crossed into the San Jacinto Fault, but go back further to 1812, and the record shows the opposite. That earthquake, centered near Wrightwood, close to magnitude 7.5, didn't stop at the junction. It crossed straight through, rupturing both fault systems together as a single event. Historical accounts link that quake to serious damage and dozens of deaths in nearby mission settlements at a time when the region's population was a fraction of what it is now. Same location, same geological ingredients. Two earthquakes, decades apart, and completely different behavior at exactly the same spot. One stayed contained, one didn't. That's the contradiction the new research set out to explain. Not whether Southern California's faults are stressed, everyone already knew that, but what actually decides whether a rupture stays on one fault or spreads across both. To answer that, Burkhard's team didn't rely on guesswork or on simply counting years since the last big quake. They built something more specific, a physics-based model that simulates the entire earthquake cycle in 3 dimensions, tracking how stress builds, transfers, and slowly relaxes over centuries. To calibrate it, they reconstructed 1,000 years of earthquake history along the southern San Andreas and San Jacinto systems, piecing it together from radiocarbon dating of buried fault ruptures, tree ring records, and historical accounts of ground deformation. The team included researchers from the University of Hawaii at Manoa, the USGS Earthquake Science Center in Pasadena, and the Scripps Institution of Oceanography at UC San Diego. This wasn't a single lab running a hunch. It was a coordinated attempt to simulate in detail exactly how much pressure has built up on each side of that mountain pass. Before going further, it's worth ruling something out. In parts of the United States, unusual clusters of earthquakes have been linked to industrial activity. Wastewater injected underground from oil and gas operations, changing fluid pressure on existing faults, most famously across parts of Oklahoma over the last decade. That's a real, well-documented mechanism elsewhere, and it's the kind of explanation that tends to surface any time a fault makes headlines. It doesn't apply here. The stress driving this study comes entirely from ordinary plate motion, the Pacific and North American plates grinding past each other the way they have for millions of years, not from any injected fluid or extraction activity near Cajon Pass. That distinction matters because it means there's no industrial lever anyone could adjust to change the outcome. The pressure building at this junction is tectonic, slow, and already in motion regardless of anything happening at the surface. And what the model found reframes the entire question. It's not simply that stress is high, it's that stress on the 2 separate fault segments meeting at Cajon Pass is now converging toward the same level. And that alignment, more than the raw numbers, is what history suggests actually opens the gate. The tool that produced this picture is called a Coulomb stress model, and the idea behind it is simpler than it sounds. Every time a section of fault ruptures, it doesn't just release stress on itself. It shifts stress onto the surrounding rock, sometimes loading nearby fault segments closer to failure, sometimes relieving them. Run that process forward through 1,000 years of earthquakes, one on top of another, and you get a running tally of how much force is currently stored on each individual segment. That's what Burkhard's team built, calibrated against the actual historical rupture record instead of theoretical assumptions. It's the difference between guessing how full a reservoir is and actually measuring the water level. Here's where the investigation gets specific. The model measured stress in megapascals, a unit engineers use to describe pressure building inside solid material. On the San Jacinto Fault's Bernardino segment, the model puts current stress at 3.6 megapascals, the highest value recorded anywhere in the entire 1,000-year simulation. On the neighboring stretch of the San Andreas, the Mojave South segment, the number sits at 2.8 megapascals. Neither number alone would necessarily set off alarms. Southern California faults carry heavy stress all the time. That's simply what a locked plate boundary looks like. What stands out is the gap between them. 3.6 and 2.8 are close. Historically, according to the model, it's exactly this kind of narrow gap, both faults loaded up near their limits at similar levels, that has preceded the ruptures capable of crossing the junction instead of stopping there. Think of it less like a wall standing permanently between the 2 systems and more like a pressure valve that opens and closes depending on conditions on either side. When one fault is under far more pressure than the other, an earthquake starting on the stress side tends to run out of room to keep going once it reaches the calmer fault, and it stops at the junction, the way Fort Tejon did in 1857. But when both sides are loaded close to the same level, there's little to stop a rupture from continuing straight through, the way the 1812 earthquake apparently did. The gate isn't a fixed structure in the rock, it's a relationship between 2 numbers that keeps shifting decade by decade as strain builds unevenly across 2 different fault systems. That distinction matters enormously because it changes what the danger actually looks like. A single fault rupture on the San Andreas near Cajon Pass would already be a major earthquake for the region, but a joint rupture, one that starts on either fault and crosses straight through the gate into the other, is a different scale of event entirely. Burkhard's team estimates a combined rupture through the pass could reach somewhere between magnitude 7.4 and 7.8, and unlike a single fault event, it would tear through a far larger stretch of ground, not just 1 fault line's worth of shaking, but 2 overlapping in the same window of time. That distinction is easy to miss if you only look at the headline number. A jump from magnitude 7 to magnitude 7.8 doesn't sound dramatic on paper. In practice, because the energy released by an earthquake grows exponentially with magnitude, that difference represents many times more destructive force, and a joint rupture spreads that force across a wider geographic footprint than a single fault ever could on its own. And the footprint here isn't empty desert. Cajon Pass carries Interstate 15, one of the primary routes connecting Southern California to Las Vegas and the rest of the interior West. It carries rail corridors used for freight and passenger service. It carries major electrical transmission lines feeding the Inland Empire. A rupture that crosses this junction wouldn't just shake buildings in Los Angeles, San Bernardino, Riverside, and the Coachella Valley. It would sever, at least temporarily, some of the physical infrastructure connecting them to each other and to the rest of the country. Picture what runs through that gap on an ordinary afternoon. Freight cars stacked with cargo bound for ports and warehouses across the Southwest. Commuters merging onto the interstate. Transmission towers stepping down power drawn from hundreds of miles away. None of that infrastructure was designed with a two-fault junction crossing rupture as its primary planning scenario, because until this study, the mechanism deciding whether such a rupture was even likely hadn't been mapped this precisely. At this point, it would be easy to assume the story is simply, the big one is coming, and it's worse than we thought. That assumption misses something important, and it's worth pausing on because this same year, a completely different research team produced a headline that sounds almost identical, and the two are not the same discovery. In 2025, a group at Oregon State University, led by marine geologist Chris Goldfinger, published evidence that two other fault systems hundreds of miles to the north, the Cascadia Subduction Zone off the Pacific Northwest and the northern San Andreas Fault, appear to rupture together, sometimes within hours of each other, based on paired sediment layers recovered from the seafloor. If you've seen headlines about two faults that could trigger each other, some of them are describing that study, not this one. It's a real, independently verified finding, but it involves a different fault type, a different location near the California-Oregon border, and a completely different kind of evidence. Sediment cores record the aftermath of ancient landslides triggered by shaking on the seafloor. Burkhard's team never touched a sediment core. Their evidence comes entirely from a physics-based stress model calibrated against 1,000 years of ground rupture history in Southern California. Picture how different the two settings actually are. The Cascadia story plays out where a 200-mile offshore subduction zone meets the northern San Andreas near the California-Oregon border in cold water, evidenced by sediment cores hauled up from the seafloor after a research ship's navigation error sent it drilling in the wrong spot decades ago. The Cajon Pass story plays out on dry land, under a desert highway past northeast of Los Angeles, evidenced by a stress model running on historical earthquake data reconstructed from tree rings and radiocarbon-dated fault trenches. Different tectonic plates entirely, different rock, different kind of proof entirely, gathered by two separate teams who weren't working together. Two legitimate discoveries, two different mechanisms, two different fault pairs, separated by hundreds of miles. The coincidence is only in the phrase faults triggering each other's, not in the geology. That correction matters because conflating the two stories would blur exactly the kind of precise, mechanism-specific evidence that makes each finding credible in the first place. So set the Cascadia story aside. The story unfolding at Cajon Pass stands on its own, and it becomes even more disturbing once you look at what happened the last time these two faults lined up this way. Go back to January 1812. The Wrightwood earthquake, estimated near magnitude 7.5, struck a region with a fraction of today's population, scattered missions, ranches, and a handful of small settlements strung along what would later become Southern California's urban core. Contemporary accounts describe cracked adobe walls, damaged mission structures, and serious loss of life in the immediate area, though records from that period are incomplete by modern standards pieced together from mission logs and later reconstructions rather than seismic instruments, which didn't exist yet. What matters for the current investigation isn't the exact death toll, it's what the ground did. According to the geological evidence, the rupture didn't stop at Cajon Pass. It propagated through, activating both the San Andreas and San Jacinto systems as one connected event, shaking a stretch of ground that today holds several million more people than it did then. 45 years later, in January 1857, the same stretch of the San Andreas ruptured again. The Fort Tejon earthquake, magnitude 7.9, one of the largest ever documented on this fault. Contemporary reports describe the ground splitting open along the fault trace for well over 100 miles, fences and roads offset where they crossed it, and shaking felt as far away as Los Angeles and the Central Valley. And yet, running into Cajon Pass from the opposite direction that the 1812 rupture had taken, it stopped. The San Jacinto Fault, sitting right there, never joined in. Let that register for a moment, because it's the closest real precedent for what Burckhardt model is now flagging as a live possibility. 2 centuries ago, under conditions the new stress model associates with narrow, converging pressure between the 2 faults, the gate opened. The rupture crossed, and the region on the other side of that crossing looked nothing like it does today. No interstate, no rail lines, no power grid, no millions of people living within reach of the shaking. But similarity is not a forecast. It's worth being precise about what the 1812 comparison actually proves and what it doesn't. It shows that a joint rupture through Cajon Pass is physically possible. History already recorded one. It shows the kind of stress alignment associated with that outcome. What it cannot show is timing. The model doesn't say a rupture is imminent, doesn't assign a date, and doesn't claim the fault system will behave exactly as it did 2 centuries ago. Fault behavior depends on more than stress alignment alone, on friction along the fault surface, on the specific geometry of the rock at the junction, on factors that remain difficult to measure directly even with modern instruments. Burckhardt has been explicit about this limitation herself. The study, in her words, is not a prediction of when an earthquake will occur. It's a physics-based picture of the current stress state, meant to sharpen hazard planning, not to set a countdown. There's another difference worth being honest about, one that cuts the other way. Southern California in 1812 had no seismic building codes, no early warning systems, no coordinated emergency response network. Southern California today has decades of retrofitting on bridges and public buildings, strict codes for new construction, and a statewide earthquake early warning system capable of sending out alerts in the seconds after a rupture begins, before shaking reaches distant cities. None of that prevents a joint rupture through Cajon Pass. It does change what survives it. The comparison to 1812 illustrates the geological mechanism, not the human outcome, and conflating the two would misrepresent exactly what the historical record can and can't tell us. That distinction is easy to lose in a headline, and it's exactly why the researchers built the earthquake gate framework the way they did. They weren't trying to predict a date. They were trying to explain a pattern that had puzzled seismologists for years, why the same junction handled 2 large ruptures so differently, and their answer, tested against 1,000 years of reconstructed history, is that the deciding factor is relative, not absolute. It isn't how much stress either fault carries. It's how closely the 2 numbers match, which brings the story back to where it started with 3.6 megapascals on one side of the pass and 2.8 on the other, closer together than at almost any point in the model's 1,000-year run. The gate isn't slammed shut. It isn't standing wide open either. It's sitting in the range where, historically, both outcomes have been possible. And the variable that will ultimately decide which one happens next isn't something anyone can currently observe in real time. So where does that leave the region right now? Start with what's actually confirmed. The stress model, built and peer-reviewed, shows record-level loading on both the San Jacinto Bernardino segment and the San Andreas Mojave South segment. The historical record confirms Cajon Pass has produced both contained and cross-fault ruptures in the past. The relative alignment between the 2 fault segments today resembles conditions associated in the model with joint rupture scenarios rather than single fault ones. What remains interpretation, not fact, is what that alignment means for timing. Researchers describe the system as critically loaded and a description of current stress conditions, not a countdown to failure. It's a phrase that describes a state the way a saturated sponge is a state, not a schedule for when the next drop causes it to overflow. And what remains open speculation is whether the next major earthquake at Cajon Pass will resemble 1857, contained and severe but limited to 1 fault, or 1812, smaller in magnitude but spread across both systems at once, or something the historical record hasn't captured at all, a scenario the 1,000-year model can bound but not guarantee. It's also worth noting that Burckhardt's team designed this framework to extend beyond Southern California. Cajon Pass isn't the only place on Earth where 2 major faults meet at a geologically complex junction. The same physics-based approach, tracking relative stress alignment rather than absolute stress alone, could in principle be applied to other multi-fault junctions worldwide, many of which have never been modeled with this level of historical detail. That's a separate ongoing line of research, not a claim this exact scenario is playing out anywhere else right now. Going forward, scientists aren't waiting passively for an answer. Continued GPS and satellite radar monitoring track how strain across the region shifts month to month, watching for whether the San Jacinto and San Andreas segments keep converging toward each other or start to pull apart in their stress levels again. Paleoseismic trenching, physically digging into the fault trace to date older ruptures, continues to refine the 1,000-year record the model depends on. Every refinement either strengthens the current picture or forces researchers to revise it, and that revision, if it comes, would be treated as new evidence, not as a failure of the earlier study. None of this happens in isolation from the region's existing early warning infrastructure. California's statewide earthquake alert system, built on a network of ground motion sensors, is designed to detect the very first waves of a rupture and push out warnings before stronger shaking arrives elsewhere. It can't say whether a rupture will cross the gate or stop at it. What it can do, if a rupture does begin near Cajon Pass, is buy seconds, sometimes tens of seconds, for trains to slow, for surgeries to pause, for people to drop and take cover before the strongest shaking reaches them. That system doesn't reduce the stress sitting on either fault. It changes what people can do in the narrow window between the ground moving and the shaking arriving. None of this means catastrophe is coming. It means the tool now exists to actually watch the mechanism that decides how catastrophic a future rupture could become, instead of relying on elapsed time and hoping the pattern holds. That's the quiet, almost anticlimactic truth sitting underneath the alarming stress numbers. The danger isn't new. Southern California has always sat on these two faults. What's new is the ability to see, with actual physics rather than assumption, which conditions have historically decided whether a rupture stays contained or crosses the line. Right now, under an ordinary stretch of interstate, freight cars roll past at highway speed. Commuters merge onto the grade without a thought, and nothing on the surface hints at what the model shows underneath. No cracked pavement, no warning signs, no visible difference between this stretch of highway and any other mountain pass in the state. That's the unsettling part of a story built on stress models instead of visible damage. The evidence lives entirely underground, in numbers on a simulation, not in anything a driver could see through a windshield. Two faults, loaded close to their historic limits, sit within reach of each other at a junction that has, at least once, let a rupture pass straight through and at least once stopped it cold. The gate isn't announcing anything. It's just sitting there in the range where history says either outcome remains possible, waiting on a variable no one can watch directly, while instruments keep quietly logging every fraction of a millimeter the ground moves next.